We finished that example. Let's introduce another vector operation. And this kind of finishes up a lot of times chapter 2 in most textbooks, ours included. Again, I'm working on the Hibbeler text. The dot product. The dot product is written like this. If I take A and I dot, so I normally just draw a big circle, darkened circle, or dot there. If I dot A with B, A dot B is how that is read. That is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And that is where the angle, that angle needs to be between 0, or it's going to give you an angle between 0 and 180 degrees. If your angle should be larger than that, you're actually going to need to look in 3 space and see if you need to add another 180 degrees to it or not. But normally that's, actually, no, it's always going to be between 0 and 180 degrees. Never mind. The angle will always be between 180 degrees, 0 and 180 degrees for this. There are all the other operations we talked about. Addition, if I add vectors together, that gives me a vector. If I subtract vectors, that gives me a vector. Notice this is a scalar quantity. So if this is a type of vector multiplication, it's not actual vector multiplication. That generates what we call tensors, which are a very different animal, higher level math and engineering for most of us. But this is a very simple form of vector multiplication, and it generates a scalar quantity. In chapter 4, we'll talk about another vector operation, vector multiplication, called the cross product. That generates a vector quantity. But here, this generates a scalar quantity. Now, what can we do with this thing? So some sub-operations we can do with the dot product, or some properties, if you will. It is what we call commutative. What does that mean? Well, it means that if I take A dotted with B, it doesn't matter whether it's A dotted with B or B dotted with A, I will get the same quantity. You can scale the vectors, meaning that if I take A, some lowercase a, some scalar quantity, and I multiply that scalar by the dot product of A and B, A dot B, then that would be the same. I could apply that scalar to either the A vector and then dot that quantity with B, or I could apply that scalar to the B vector. So A dotted with little a vector B. And that would be the same quantity. So if I've got a scalar, I can apply that scale to either vector and then dot the result with the other vector and proceed accordingly. This also follows a distributive property. Use a distributive property with the dot product, meaning that if I take A and I dot A with the resultant of B and C, so if I add B and C together, then that would be the same as if I took A and dotted it with B and added that quantity to A dotted with C. So I can distribute this A dot into the B plus C quantity. Okay, so those are the rules so far. Again, A dot B gives us a scalar quantity. Now, recall, what do I mean by that? A dot B, again, recall, by definition, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. If theta equals 90 degrees, notice what happens. A dot B If I take the cosine of 90, I get 0. If A and B are parallel, if A and B are parallel, then A dot B just equals AB. Because basically we're saying the angle between them is either 0 or, we're saying the angle between them is 0 if they're parallel. Then it's just AB. So, notice what happens if I take these standard unit vectors. If I take I dotted with I. Well, those are parallel. So then I would just take the magnitude of I times the magnitude of I. Well, both of these have a magnitude of 1, so that is 1 times 1. And I get the same thing if I dot any of these unit vectors with themselves. I'll get 1. So j dotted with j gives me 1. K dotted with k gives me 1. Notice if I take I dotted with j, well, those are 90 degrees apart. If theta is 90, this gives you 0. Same thing if I took I dotted with k, that's 0. And if I took j dotted with k, that's 0. I think that's all the combinations. Maybe there's more, but I think that's it. So, what does this mean? Well, if I take all of these together and I combine them all together, right, the fact that I can do a scalar operation, distributive, and this concept that a unit vector dotted with itself gives me 1, and a unit vector ij or k dotted with any other unit vector gives me 0. Notice what happens if I say, well, let's expand this out. If I take A and I dot it with B, again, this is L3 and this is page 4 of something. If I take A dotted with B, and if I break this down into, if I resolve this vector, these vectors, both these vectors, into their components, AX in the I direction plus AY in the J direction plus AZ in the K direction, that sum, that's the A vector, that's going to get dotted with bx in the I direction plus by in the j direction plus bz in the k direction. Dot those two vectors together. And again, we're going to involve, I've got scalars multiplied by vectors. I'm going to apply the distributive property here, and we're going to go nuts with this thing, right? So what happens then? Well, this is what you get. A dotted with B. You're basically foiling out a 3-term polynomial with a 3-term polynomial, and it's not FOIL. It's, you're going to go through the distributive property. But what you end up with is you end up with AX in the I direction dotted with each of these three in the B terms. So it's going to be dotted with BX in the I direction plus AX in the I direction, dotted with BY in the J direction, plus AX in the I direction, dotted with BZ in the K direction. And I'm going to write this on the second line. So this goes on, right? I've done this. I take this and I dot it with all three of these. Then I need to take this, the Y term, and dot it with all three of these. And then I need to take the Z term and dot it with all three of these. So I would have AY in the J direction dotted with BX in the I direction plus, and then I need to do that with AY dotted to BY, AY dotted to BZ. And then add to that, then I need to do AZ in the K direction. I'm saying here, I'm not going to write all these, right? But just to give you the idea. AZ in the K direction is going to get dotted with, and you can find this in your book where I think they will typically go into more detail, but we're going to take these Z terms and dot it with each of these. So AZ in the K direction dotted with BX in the I direction plus We'll do the same thing. I'd take AZ dotted with BY and AZ dotted with BZ. And so I'd have 9 terms basically going on there. 9 sets of dot terms. What's going to happen? Well, notice I dotted with I, this is 1. So I'm going to have AX times BX. And then here I'm taking I dotted with J, that's 0. I dotted with J is going to be 0. So I dotted with J is 0. Here this is I dotted with K, that's 0. This is J dotted with I, that's going to be 0. In here I'm going to have AYJ dotted with BYJ. That one's going to be AYBY. So a bunch of these are going to be zeros. You're going to have some that are not 0. The ones where I'm dotting the component with itself, and you end up with AX BX plus AY BY plus AZ BZ. So I can find the dot product actually a couple of ways. This is one way I can find the dot product. If I know the x, y, and z components of both of these vectors, I can just do that. Hi, Izzy. We're busy. Just a second. This is also equal to AB times the cosine of the angle between them. Okay. That's kind of cool. So what does that do? This allows me to... Okay. Come here. Come here. I apologize. Come here. Oh, Izzy. Say hi to Izzy, everybody. All right. Sit down. If I don't put her on my lap, she's just going to yell at us the whole time. You can find the angle now between two vectors easily. If I know the x, y, and z components of two vectors, I can find their magnitude easily enough. And then if theta is the only unknown, if the angle between two vectors is the only unknown, but if I can describe the two vectors in x, y, z coordinates, much like I did back here, I described that vector in x, y, z components. So if I have two vectors in the same x, y, z coordinate system, I can find the angle between them using a dot product. Right? It also the dot product is a very powerful tool because it will give you the projection of one vector on the other. What do we mean by that? So there's 2 points here. Easily find the angle between two vectors. And also, another thing the dot product does for us, it allows us to figure out how much of a vector is in the direction of another vector. What do I mean by that? If I've got a vector here, we'll call it A, vector A. I've got some other vector here, we'll call him B. There's some angle between them, theta. What I can do is I can say, well, I could draw an imaginary point right here where I would find a right angle between those two vectors. And then I would have a length right here. And that length would be AB cosine of the angle between them, which is A dotted with B. So notice what I'm saying here is I can find what we call the projection. The projection meaning how much of a vector is in the direction of another vector. Right, so here I can figure out how much, this quantity represents how much of vector A points in the direction of B. And I could go vice versa. All right, that's a nice stopping place. We'll pick up on the next one.